I like to think of black holes as the ultimate roach motel in the universe. Once you go in, you don't go out. Ugh. But beginning with the work of Stephen Hawking, we realize that, don't worry, dude, you're in this episode a lot. We realize that black holes emit radiation. They actually glow just a little bit, and they eventually dissolve, completely disappearing. And this opens up a nasty paradox called the black hole information paradox. What happens to all the information that flows into a black hole after it disappears? The full answer relies on a complete description of quantum gravity, which we don't have. Let's take a step back. In Einstein's theory of relativity, black holes are extraordinarily simple objects. You just need only three numbers to completely describe any black hole. You need to know its mass, its electric charge, and its spin, and that's it. And then the black holes themselves are extraordinarily simple. There's a singularity at the center, which is a point of infinite density and also the subject of another episode. And then it's surrounded by an event horizon. That is the boundary, the entrance to the Roach Motel. But that event horizon is even more boring than you think it might be. Take a look at this waterfall. Where is the point of no return? It's not the waterfall itself, it's somewhere upriver. There's a place on the river where the flow is too strong for you to be able to fight against the current. That is the event horizon. That is the point of no return. And this shows us how boring event horizons really are. They don't look any different from any other part of the river. You only discover them when you try to escape. But Stephen Hawking found that event horizons are anything but boring. There's a weird interaction happening there between the event horizon itself and the quantum fields that surround it. And this interaction gives rise to the emission of particles that have a temperature. Black holes glow. And that's really messed up. So let's go to the chalkboard to check this out. Stephen Hawking's result was extraordinary and honestly counterintuitive. Who knew that black holes, the ultimate bottomless pits of destruction, would glow, would have a temperature? And this temperature is something that we can calculate. Hawking's formula for the temperature of a black hole is simply temperature is equal to the reduced Planck's constant, which is Planck's constant divided by 2 pi, times the speed of light cubed divided by 8 pi, Newton's gravitational constant, times the Boltzmann constant, times the mass of the black hole. This is telling us that the temperature of a black hole is incredibly small because the mass of a black hole, even the smallest black holes have a mass of a few times that of the sun, makes this a very, very big number, which makes temperature a very, very small number. So this is incredibly, incredibly small. We're talking a typical black hole emitting, like 1 or 2 photons a year, but it's not zero. Now, black holes emit radiation through this crazy complex quantum mechanical process. Any kind of radiation has a spectrum, has a structure. But to describe the radiation emitted by a black hole, I need some sort of inspiration, a light bulb moment, if you will. Thank you. All right, this is an old school incandescent light bulb, and the kind of radiation, the spectrum of radiation emitted by this light bulb is something we call black body radiation. Now, light bulbs aren't the only thing in the universe to have black body spectra. Human bodies emit radiation with a similar spectrum. The sun emits radiation with the same spectrum. And so do black holes. Let's say we have a very cold object. Very cold objects have a black body spectrum of flux versus wavelength that looks something like this. And very hot objects have a similar kind of spectrum, but it's shaped more like this. It's peakier, and then it goes down like this. Any object in the universe that emits as a black body radiator will have something looking like these curves. including black holes. That's one of the most remarkable things about Hawking's result, is how simple the radiation emitted by black holes really is. It's this crazy complex quantum mechanical process that leads to a simple equation for the temperature and then a well-known spectrum that we've known about for over a century. But that simplicity makes black holes even more confusing, because this is the exact place where the paradox comes in. Because the black body radiation emitted by a black hole doesn't carry any information. It's very boring, actually. So let's say you make one black hole made out of, I don't know, a potato. All right. And you make another black hole made out of a plant. Oh, yeah. So I've got two black holes. One is made out of potatoes and one is made out of plants. A lot of potatoes and a lot of plants, but you get the idea. There's a lot of information in this plant and in this potato, and it's locked up in the black hole. But then the black hole starts radiating. And they have the exact same mass, they have the exact same temperature. There's exact same black body radiation. There's no information carried away. I don't know which one is the potato black hole and which one is the plant black hole. But as they radiate, they lose mass and eventually they disappear. So where did the information go? What happened to that? This is the paradox. So let's talk to an expert to dig into this mystery a little bit more.
I am Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a science communicator.
Well, let's talk about space then. We're talking about black holes. The universe makes stars, and some stars turn into black holes. How does that happen? How do you go from this giant ball of radiation and light and warmth to a black hole?
Black holes can form in a few different ways. Astronomers are still trying to figure out how the very first or early big black holes formed. We call these primordial black holes. But the most common way for black holes to form is through the life cycle of stars. So if you have a star that's massive enough, let's say it has to be about 40 times more massive than our sun. By the time it runs out of all of the hydrogen in its core, something called hydrostatic equilibrium breaks. So the way that stars work is that they're constantly in balance between gravity crushing in and the pressure that you get when you have nuclear fusion pushing out. And when you stop fusing hydrogen in your core, you lose the outward pressure. So gravity forces the star to collapse in on itself. And then there's this rebounding effect that creates a supernova explosion. So in the explosion, a lot of the material from the star gets flung out from the system. But what's left, if it's dense enough or if it's massive enough, is a very dense black hole. These are small black holes. They're called stellar mass black holes, only a few times more massive than our sun. But if you get enough of them together, then they can grow into a bigger black hole.
How many black holes are we talking about in a galaxy? 1, 2, maybe 10?
We have one supermassive black hole in the Milky Way galaxy, but there are tens of thousands of these smaller stellar mass black holes in the Milky Way alone. And there are hundreds of billions of galaxies, so there are lots of black holes out there in the universe.
You mentioned this supermassive black hole in the center of the Milky Way. How do you get something to be supermassive?
And I think in a lot of space contexts, astronomers are still trying to figure out how these really massive black holes form, but we are pretty sure that at least regular supermassive black holes, not these like hypermassive ones, that they form through galactic collisions. Because a lot of galaxies, most galaxies, have black holes at their centers. And that's just another effect of gravity. This really heavy thing is going to sink towards the center of the galaxy. And when these galaxies collide, so do their black holes, after many millions of years of spinning in towards each other. When you get all of these black holes colliding, then their masses add up. So you get a supermassive one in the center.
These black holes, they just sit there minding their own business and they don't do anything else, right?
Oh, I wish. Well, it actually is a common misconception that black holes suck things into them. And they do have very strong gravitational pulls, but they aren't like vacuums actually suctioning stuff in. It's just a gravity well. It is a pit for stuff to fall into. If we look at the anatomy of a black hole, there's the black hole in the center, and the edge of the black hole is called the event horizon. After the event horizon, if the black hole is massive enough and active enough, it has something called an accretion disk. So this is the disk of material around the black hole that it's eating. It's material that has been gravitationally attracted to the black hole and is actively in the process of spinning into this gravity pit. Sometimes there's enough friction and heat in that accretion disk that it lights up. So we can see it. That's how we study a lot of black holes, or we study their gravitational effect on things around it, like the stars that are orbiting it.
One of the things we're exploring in this episode is Hawking radiation.
Ooh.
Can you just talk about Hawking radiation and how annoying it is?
Yes, I can. So we say that black holes are so dense that nothing can escape them unless they're traveling faster than the speed of light. But that creates this paradox, because black holes have energy and they can dissipate that energy. But if something can't escape a black hole, how can it possibly dissipate this energy? Stephen Hawking came up with this hypothesis for radiation that gets trapped basically on opposite sides of the event horizon. Some get sucked in, some doesn't. The stuff that doesn't get sucked in can be radiated away as energy, as this Hawking radiation. Yeah, I've been thinking a lot about the long-term end of the universe. And one of the potential ways that the universe could end is in the big freeze. This is the scenario where the universe keeps expanding forever, long enough that all of the gas gets made into stars, and then all of those stars die and they cool off. And eventually, many, many trillions of years from now, the only thing left in the universe is black holes after all of the stars have cooled down to dark chunks of rock. So some scientists have tried to figure out what happens after that. How do the black holes lose energy? Because the only way for the universe to really be dead is for there to be no energy in it. So one way that black holes can lose their energy is through this Hawking radiation. And it would take many, many billions of years for a single black hole to lose all of its energy through Hawking radiation, but it is theoretically possible.
So the ultimate fate of the universe rests in understanding Hawking radiation.
The ultimate fate of the universe in this one potential scenario.
Thank you, Moiya.
Yeah, thank you.
To achieve his result, Hawking combined our understanding of gravity, which is general relativity, with our understanding of the very small, which is quantum mechanics. But he only did that in an approximate sense. He assumed that the gravity was relatively weak at the event horizon, that it didn't couple strongly to the quantum fields that were there. It could be that in a full theory of quantum gravity, something much more complex is happening at the event horizon, something we call a firewall. Now, studio regulations prevented me from having an actual wall of fire to show you what would happen, so instead, I'm just gonna smash some eggs. The key idea here is that in physics, information is preserved, and everything can be traced back to its roots. If I smash this egg, all the information is preserved. If I wanted to, I could retrace all the steps of all the molecules and reconstruct the egg. It would be extraordinarily difficult, but it wouldn't be impossible. So what happens in firewall theory is that if this egg were to hit the event horizon, it would get obliterated and all its information would be spread across the event horizon. And then that information would get tangled up with the Hawking radiation leaking out into space. That way, when the black hole disappears, all the information is still there in the universe and the paradox is resolved. A little bit messily, but still resolved. You know, this is actually oddly satisfying. Anyway, we should move on. Is there someone here to clean it up, or? It's me. It's me. Okay. As intriguing as firewall theory is, it does have its shortcomings. Most importantly, we don't actually know how it works, how the information actually gets encoded on the event horizon, and how it gets tangled up in the Hawking radiation. So it doesn't actually solve the paradox, it just moves it somewhere else. But in our studies of black holes, we found something very intriguing. And that has to do with holograms. Yeah, holograms, but not the holograms you're thinking of. Holographic theory, where multidimensional information is stored on a lower dimensional of the substrate, if you will. We found that when information flows into a black hole, its surface area increases in proportion to the amount of information, not its volume. So this is telling us that somehow the information that goes into a black hole is getting stored or encoded on the surface area, not within the bulk of the black hole itself. What is this telling us? Well, we're not exactly sure. It could mean that a full theory of quantum gravity really only lives in 2 dimensions, not 3, or something else. I mean, honestly, black holes are just plain confusing. Thanks, Steven.